Alright guys, so in the last video we talked about cylinder head and camshaft selection. I want to go just a little bit deeper into the camshaft portion of things. This is a part that a lot of people get confused on whenever they're trying to buy a camshaft or they're trying to design or develop a camshaft for their application. Now granted, the ramp rates and how the lobe is exactly designed, we're not going to go into that. However, if we're going into this as a perspective of, hey, I'm buying a camshaft for my application and I need the right valve timing events, okay? So I threw up here Old Red's camshaft specs so that we can just use it as an example. Okay, so if you look up the top left-hand corner, I've got this separated, building and buying. When I say building, again, we're not talking about ramp rates and the actual lobe characteristics. However, we are going to go into the valve timing events, which are the most important. Okay, so we talked in the last video, intake valve open, intake valve close, exhaust valve open, exhaust valve close. Okay, and what they mean and their somewhat significance, okay, because there are caveats to both. One thing I want to go over is if I'm trying to develop a cam and I get my valve timing events that I want, how do I look into a catalog and say, hey, which one does this match? Okay, so assuming all I'm given is the valve timing events, okay, so I want to close my intake valve 41 degrees after bottom dead center, based off all of my formulas and calculating what my cylinder pressure, my dynamic compression ratio would be, those kinds of things, and I determined 41 degrees after bottom dead center is where I wanted to be. So I choose that point. All right, how much overlap do I want? Okay, not super important here, but again, depending on how much overlap you have can determine how high an RPM you be able to go. I mean, it'll also determine, again, cylinder pressure. I'm not going to go into everything I went over in the last video, but basically you can have too much overlap. That's true. However, overlap's not a bad thing. And it's misunderstood, and I can go into that individually with anyone who's curious about overlap. There's tons of videos out there from reputable places about overlap and its significance in the scavenging event. More importantly, on a naturally aspirated application that get that perfect. On a boosted application, again, overlap is still needed. A lot of positive displacement blower cams out there will have almost no overlap or negative overlap, and that's a good for a stock motor. But again, if we're trying to build power, we need that overlap event. We need that scavenging event to help with getting the exhaust gases out and cleaning our cylinder out. So anyway, without further ado, so what we're going to talk about here is how do I get from the valve timing events to the actual specs that you will see on websites to buy. Okay, so looking at the left side, okay, we got our our 4 timing events that we've determined we want to have. Okay, I wanted to have 16 degrees overlap. Okay, based off my formulas, that's where I decided. And exhaust valve, I wanted it to open at 55 degrees before bottom dead center. Now again, I'm using a software where I can actually see the velocities in the port. Obviously, this is computational fluid dynamics, and you know, this is kind of being able to somewhat calculate what the velocities are and determining at that point in time, cylinder pressure has kind of bled down to the point where I still have enough that I can use it to help get the exhaust gases out, but I'm not wasting cylinder pressure that's actually being used to make torque. Okay, so that's what I determined. So those are my 4 points. So what I'm going to do is take the intake duration, okay, or to calculate the intake duration, I'm going to take 180 degrees plus my intake valve open and my intake valve close. So that's 230 degrees. So there's my duration on the intake. Same thing on the exhaust. 180 degrees plus 55 plus 7, 242 degrees. All right, so I'd be looking for a camshaft with 230, 242 duration at 50 thousandths lift. Okay, intake center line. All you're going to do is take 230 degrees divided by 2 minus 9. Okay, intake valve open. And that's 106 degree intake center line. Same thing on the exhaust center line. 242 degrees divided by 2 minus your exhaust valve close event, which is 114 degrees exhaust center line. Lobe separation angle is just your intake center line plus your exhaust center line divided by 2. So 110 degrees. So I'd be looking for a camshaft 230 degrees, 242 degrees on 110 degree lobe separation angle. Okay? Depending on who the cam manufacturer is will be what they say for the actual how many degrees advance that cam is ground on. So on this one, I would want a 230, 242 at 50, 110 degree lobe separation angle with 4 degrees of pre-ground advance on the cam. That way I can install it straight up and it would be exactly on the timing events that I want. Okay, that's how you go to buy one. If you built the cam in, I not say building it, I guess it's not the right term, but you chose your valve timing events. That's how you derive all of the things that'll be in the catalog to buy. Okay, now if you're buying a cam and you're looking for cams and you're looking at catalogs of cams and you're trying to determine, well, I don't really know what valve timing events I need. These are a bunch of cams that are available. Tristan put a video out there on kind of where I want my intake center line to be and where I want my intake valve close to be, but I don't really know what the overlap needs to be or any of that kind of stuff. So you calculated those things, so you have some numbers that you're looking for, some target points that you're looking for intake valve close and your intake center line and your exhaust center line angle, right? So we did some of those formulas. So I know what I'm targeting, but I don't actually know how to pick the points. So I'm going from a buyer side. All right, so these are the cam specs that you're going to have on the website. 230, 242, 4 degrees advance, 110 degrees in lobe separation angle. Okay, you may not be given the intake center lines, but you know you can calculate the intake center line given the advance. Okay, so those are easy to calculate. So buying, this is how you turn it into the valve timing event so that you can say, okay, yeah, that's appropriate, or no, that's too big, or well, that's too small. Okay, so intake valve open, 230 degrees divided by 2 minus your intake center line is 9 degrees before top dead center. That's intake valve open. Look, that matches. Okay, I use the same cam specs just to show how they transfer over. Intake valve center, 230 degrees minus 180 degrees minus 9. Okay, that's the calculated 9 before top dead center. That gives me 41 degrees after bottom dead center. Look, that matches. Exhaust valve closed. You got 242 divided by 2 minus 114 degrees equals 7 degrees after top dead center. Exhaust valve closed. I put exhaust valve closed twice, but let me fix that real quick. Don't want to confuse anybody. Okay. Alright, so exhaust valve open, 242 minus 180 degrees minus the 7 degrees we calculated for exhaust valve close is 55 degrees before bottom dead center. Okay, so that's how you take specs that are in a catalog and turn them into the valve timing events. Okay, depending on which way you're going after your camshaft selection, these are the two different methods you can determine how to get one or the other. Okay, I'm choosing my valve timing events. Okay, now I need to know what it looks like in a catalog. Or I don't know what timing events I need. I know that I have a couple of targets such as intake center line and exhaust valve or intake valve close and exhaust center line just based off what Tristan was talking about. So I have some kind of target. Now I need to turn that into an actual camshaft. So you find a bunch of cams that seem to be pretty close based off the duration figures, and you turn that into your valve timing events. You go, okay, yeah, that's really close to what I determined I needed to have. Okay, one is a derivative of the other. Okay, people talk about lobe separation angle, and they talk about it like, oh, you have to have this lobe separation angle for a boosted cam. You got to have 213 degrees and up and wider, 214, 215, 217. Some of these LSA cams have 220 degrees lobe separation angle. Okay, yeah, that's going to help with idle quality and vacuum and all the things that you need for a stock car. But if you're trying to make power and you don't really care about that stuff, and you have ways of mitigating it, like on Old Red, I have 16 degrees overlap. Well, I only have about 10 to 12 degrees, or 10 to 12 inches of mercury of idle vacuum. That's not enough for power brakes, so I have a vacuum reservoir to help with that. Okay, if you don't mind doing that, then you can go bigger on your camshaft. Again, I'm a positive displacement, but I have 16 degrees overlap. Is my boost pressure lower? Yes, but remember, boost is a measure of restriction in the intake. Okay, your air has something called, one thing I want to make sure I hammer home is intake valve close does determine dynamic compression, and it does determine cylinder pressure at low speed. Okay, low speed torque. The higher that number, the higher low speed torque you're going to have, but you're going to limit yourself on high RPM power, because remember, you want to have that intake valve close at the right point in time. Okay, if you have the intake valve closed too early because you're like, oh, that's going to make my dynamic compression so much higher, remember, dynamic compression is just one number. Okay, it's not the end all be all. It's just one number. And you don't need to pick a camshaft just based off of that. You need to look at everything. Air has density, okay? And when you're using a positive displacement, any kind of artificial atmosphere, all you're doing is changing the density of the air. So the higher the density, the higher inertial force it's going to have. The greater it's going to want, it's not going to want to slow down as fast, okay? On a naturally aspirated application, intake valve close is super critical, okay? On a boosted application where you have artificial atmosphere in there, you have higher inertial filling because that mass is greater, so it takes a greater pressure to slow down that mass. Okay, so as the intake valve is going back up in the cylinder, you got to close it when the inertial filling stops, when the pressure in the cylinder is greater than the intake port pressure. That's when you want to close it, because it's all about differential pressure. Okay, remember, differential pressure. If the pressure in the intake port is greater than the cylinder, you can continue to open that intake valve. Okay, but at the point in which the pressure in the cylinder is greater than the pressure in the port, you're going to have reversion. Okay, so remember, you can open that valve longer on a boosted application because you have a higher mass, you have inertial filling of that cylinder. It's going to take a greater pressure in the cylinder to overcome the pressure in the intake manifold. So just remember that. Again, Old Red, I said have greater than 7.5 to 1 dynamic compression. Old Red has 6.9, but how it will make a lot more power than if I were to have put it at 7.5. So if I would have closed the intake valve at 35 degrees before bottom dead center, or after bottom dead center, then I would have a little bit more low speed torque, and I'd have greater cylinder pressure, and I'd have less knock resistance. However, I would lose out on some high RPM power. So it's a balancing act, guys, and the math is great, but again, if you really want to get into this, you got to get a flow bench. You got to be able to do some velocity tuning, and remember that the flow bench is just a tool. It's not the end all be all. When I say put your manifold on there and put your air filter on that and get your net flow at 28 inches of water, using these formulas will get you very, very close at what you can expect for power or power potential out of that application. But you still got to get the camshaft right. You still got to get the exhaust right. You've got to get, we didn't talk a lot about exhaust, but the primary pipe diameter has to be correct for the flow. And again, the flow bench is just a tool, but you got to put the entire header that you're going to run on that application and run it and get those numbers and make sure you tune that primary pipe diameter for the right size. Anyway, that's going a little bit outside the scope of this video, but I just wanted to show you guys the two ways of determining the valve timing events, turning the valve timing events into numbers that are in a catalog, and taking the numbers in a catalog and turning them into valve timing events. I hope this was helpful. Have a good one.